Hello, this is Coordinate Calculus Part 5, Finding the Derivative. We'll be talking about evaluation and manipulation rules of derivatives and finding derivatives of certain functions with limits. Okay. So, some quick evaluation rules we'll be looking for today. We already know that if f of x equals to c, for some constant c, then f prime of x equals to 0 for all x, because that's just a horizontal line and the slope will always be 0. And then we'll be looking to prove some evaluation rules for x to the n, sine and cosine, and e to the x. And then some manipulation rules. We have that if f of x, if f prime of x is the derivative of f of x, then for some constant times c times f of x, then we can say that the derivative will be c times f prime of x. And furthermore, we have that the derivative of f of x is f prime of x plus the derivative of g prime of x equals to the derivative of f of x plus g of x. We won't be doing proofs in this episode for these manipulation rules, but this is things you can assume that will be true. So let's prove x to the n. So as many of you guys could have guessed, the derivative of x to the n equals to n times x to the n minus 1. But let's just prove this real quick. So we have that this equals to the limit as delta x approaches 0 of x plus delta x to the n minus x to the n over delta x. And we can expand this x plus delta x to the n with the binomial coefficients, binomial expansion. So this will equal to x to the n plus n choose 1 times x to the n minus 1 delta x plus n choose 2 x to the n minus 2 times delta x squared dot 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 all the way till n choose n minus 1 x times delta x to the n minus 1 plus delta x to the n, and then we'll have a minus xn at the end from here, and then this is all going to be over delta x. And we can notice how the x to the n's will cancel out, so we're left, and then we're left with this big mass here, and we're gonna pull this part out. So remember, by continuity we can add and subtract limits and pull out limits from each other. So this equals to the limit as delta x approaches 0 of n times x to the n minus 1 times delta x over delta x plus the limit as delta x approaches 0 of n choose 2, this is a 2, n choose 2 times x to the n minus 2 times delta x squared plus n choose 3 times x to the n minus 3 times delta x cubed all the way till delta x to the n, right? And this is all going to be over delta x. And from here we notice this right hand side of the expression, that there are we can pull out a delta x from everything on the top, and basically everything else will be left with the delta x still. Everything power is greater than 2, so delta x squared, delta x cubed, all the way to delta x. And if we divide by delta x, each term will have a delta x left, and we know that delta x approaches 0. So this will just evaluate to 0. I hope you can see that. And then with this left-hand side, we'll just have limit as delta x approaches 0 of n times x minus 1. And since this doesn't really rely on delta x, this just equals to n times x to the n minus 1. So that's our final answer, and that's our proof. It's kind of simple. This was kind of a little informal, but I hope you'll understand where the delta x's cancel out and where they'll be left. Okay. So let's do cosine of x first. So proof cosine, or actually let's do sine first. Sine of x. Okay, so for this, so d dx of sine of x will equal to the limit as delta x approaches 0 of sine of x plus delta x minus sine of x over delta x, right? And you can do your sign addition formulas to get limit as delta x approaches 0 of sine x cosine delta x plus cosine x sine delta x minus sine x over delta x. And we can evaluate this. So we can let's do this more steps. So we can put this sine of x into here to get limit, or basically like reverse distribution. Limit as delta x approaches 0 of sine of x times cosine of delta x minus 1, right? You see that? Plus cosine x sine delta x over delta x. Alright. So as delta x, you can just say as delta x approaches 0, we know that cosine of delta x will approach 1 because cosine of 0 equals 1. And so therefore cosine of delta x minus 1 approaches 0. So this limit therefore becomes the limit as delta x approaches 0 of cosine x times sine of delta x over delta x. And as you might have known, sine of delta x over delta x approaches 1 as delta x approaches 0. So this just equals to cosine of x. This part may require more formal proofs, but if you learn pre-calculus, you will probably have heard that as delta x approaches very small numbers, sine of delta x equals to delta x, so this is approaching to 1, this fraction. So we're left with that the derivative of sine of x is cosine of x. And this sort of makes sense if we draw out our functions. Right, sine of x kind of looks like that. And cosine of x kind of looks like that. Something like that, right? So we can notice here that somewhere here this would equal to 1, which makes sense. And then at pi over 2, when the sine is at its peak, cosine is 0, and so therefore sine of x derivative, the slope here will be 0, which makes sense. And then at pi, cosine will be at -1, and so there will be kind of like a negative slope there. It kind of makes sense, right? So we see that in general, this derivative makes sense. So the sine of x, derivative of sine of x is cosine of x. And we'll do a quick proof of cosine of x. So d dx, so this is cosine x proof. d dx of cosine of x equals to the limit as delta x approaches 0 of cosine of x plus delta x minus cosine of x all over delta x. And this equals to the limit as delta x approaches 0 cosine x cosine delta x minus sine delta x sine x minus cosine x all over delta x. And this is your cosine addition formula, and then we can just do the same thing we did for sine. So cosine x times cosine delta x minus 1 minus sine of delta x sine of x over delta x. This will just become 0 as we said before. So we're left with limit as delta x approaches 0 of negative sine of delta x sine of x over delta x. And as before, we said that this approaches 1, so this equals to negative sine of x. And if we look back into our graphs here, the slope of cosine here is negative 1, while sine is positive 1. So this is negative. This slope might be negative 1 when sine is 1. That makes pretty much good sense. So we've proven that the derivative of cosine equals to negative sine of x. Now for e to the x, we'll start off with a definition from the pre-calculus. Remember that e equals to the limit as, let me see, we can say that as h approaches 0 of like 1 plus h to the 1 over h. That's our pre-calculus definition of e. So we'll use that for d dx of e to the x. So we don't really know much about this, but we'll just start off with limit as delta x approaches 0 of e to the x plus delta x minus e to the x all over delta x, which equals to, we can pull out a whole e to the x here. So this equals the limit as delta x approaches 0 of e to the delta x minus 1 over delta x. Alright, so now we seem to be a little bit stuck because we don't really have any like evaluation rules for e to the delta x over delta x. But if we look back to here, we can say that for small h, e to the h roughly equals to 1 plus h. We just raise both sides here to h power, right? So you raise this to h, you raise this to h. The exponents will cancel on this side, and you're left with 1 plus h roughly equals to e to the h. So we can say here that e to the delta x roughly equals to 1 plus delta x, right? So this limit will become e to the x times the limit as delta x approaches 0 of 1 plus delta x minus 1 over delta x, which equals to e to the x times the limit at delta x approaches 0 of delta x over delta x, and this will just equal e to the x. So that was a pretty neat proof of the derivative of e to the x is just simply e to the x. So we draw our function here, e to the x, this is 1, so it's going to look something like this. So for any point, say 2, this is e squared. The slope will also equal e squared. That's how e to the x is special. So we can also define e to be the real number that satisfies that its derivative. When you raise it to x power, its derivative is e to the x. That's another way we can define e in calculus instead of pre-calculus. So that's it for finding the derivatives of special functions, and we'll be back with some more derivative rules.